So multivariable functions were those that have two variables in them. And remember, we found that we could take a derivative with respect to one of the variables. And we did that by keeping the other variable or considering the other variable as a constant. And so with two variables, we were able to find two first partial derivatives. Then we found that we could find two second derivatives for every one partial derivative. Will we do more than two variables? Yes, we're going to do more than two variables today. But it won't, it's fun. Oops. So we found that we could find a second derivative with respect to the same variable as the first derivative, and we can also find a second derivative with respect to the other variable, right? So we got quite a bit of practice with that. And so it's kind of like a genetic tree, right? Where we have ways of finding two second derivatives. And we determined that in order to find extrema, and our extrema, remember, represent maximum or minimum points, we really needed those second derivatives in order to determine what type of extrema we had. So we have this m factor, which is found by multiplying fxx by fyy and subtracting fxy squared. And we found that if m was greater than 0, we had an extrema of some type. Do you remember that? It just said, oh, we have an extrema. Then if we looked at the two second derivatives, fxx and fyy, if they were greater than 0, we had a minimum. And if fxx and fyy were less than 0, we had a maximum. Do you remember that? So that's how we were able to find extrema in that last example that we did last week. Okay. And so this is just a little summary of what I'd said. So again, fxx, if it's greater than 0, we have a minimum. Fxx less than 0, we have a maximum, and so on. Okay? So in the questions we do, they're, business application questions. We're going to be looking at extrema, either maximum or minimum points. And if you're operating a business, of course, you want to maximize your revenue, maximize your profit, and minimize your costs. So those are kind of the general things that you're going to expect, right? Okay, so let's have a look at this first question. It looks like it's not centered. There we are. So our extrema. So here we have a question. It says, the most significant expenses for a particular house cleaning service are transportation and labor costs. The daily profit in dollars for the business is approximated by this function. This is the function we're working with. X is the cost of a gallon of gasoline, which, if you'll notice, gasoline prices are going like crazy right now. And Y is the hourly wage paid to housekeeping employees. So it says, part A, find and interpret P sub x of xy and P sub y of xy. So those are the first derivatives with respect to each of the variables. So first we have to find what they are, and then we're going to interpret what they mean within this profit function. function a little bigger. And try and stay on the board. There we are. So the first thing we do is find p sub x of xy. So that means we're looking for the derivative with respect to x, which means we're considering any other variable in the function as a constant. So the only other variable is y. So we're considering y a constant. And so 600 is a constant, derivative is 0, minus 2x cubed. Derivative there is going to be minus 6x squared, plus 6xy. The derivative is plus 6y, and minus y squared. There's no x in that term, so that is a constant, derivative is 0. And we do the same for the first partial derivative with respect to y. Same thing, we have 6x minus 2y. Okay? So now we're supposed to interpret what this means. So the interpretation within the context of the question really reflects what you do mathematically. So in this first derivative with respect to x, right here, it means that gasoline, the cost of gasoline is changing. Remember, we have rate of change, marginal, right? So the cost of gasoline is increasing where the wage is staying constant. Right? Does that make sense? Think about what you did mathematically to find that first partial derivative. So then if we look at p sub y of xy, interpret that within the context of the question. What does that mean?
Sorry, I just had a question.
Yeah.
And since it's like a negative 6x, wouldn't it be that the cost is okay? Because I guess in this case, negative is cost increasing, right?
Yeah, and depending on the values of x and y, right, we might still see that, the profit will be going down with an increase in gasoline cost and keeping the wage constant. That's what I seem to be seeing here, right? So we have to see.
If it was, hypothetically, if it was plus 6x squared, would you say then that the cost of gasoline is going down by 6, or no?
No, it's looking at the rate of change of the profit when the cost of gas is going up and the wages are staying constant. You're still looking back at profit and those two factors that contribute to the profit. Right? So P sub X is the change in profit when gas goes up by 1 unit per, I don't know, whatever, I guess it's here per gallon, and where the wage is kept constant at some value. And the P sub Y is the rate of change of profit when the cost of gasoline stays the same and the wage goes up by $1 an hour. Does that help?
Yep.
Okay, it's all reflecting back to how the profit is impacted by these changes. So here P sub Y then, right, that is when the cost of gasoline is constant and the wage goes up by 1 unit. So it'll be, it's hourly wage, so it'll be $1 an hour. Yeah? So then it says for B, find all critical points. And really what that means, it's another word for saying find the values of X and Y that are going to maximize the profit. Critical points is just the sort of math term for that. So remember when we did that one example last week, we found that we could use the same kind of techniques as we did when we were solving 2 equations with 2 unknowns, right? We used elimination, substitution, or graphing. And so let's look at what we do next. So we found the 2 first partial derivatives. don't know why this is something persistent in my, uh-oh, it just dropped, didn't it? Oh dear. So we can solve these two equations with two unknowns using substitution or elimination graphing. Nobody likes to do graphing apparently. So let's set up these two equations. And remember, we're setting them equal to 0. Our two partial derivatives. And generally when we were looking at two equations and two unknowns, they were both linear equations. Remember that in week 3 or 4? So we have something different here. Our first partial derivative is a quadratic, minus 6x squared. But I think we can look at this second partial derivative and try a substitution method. Because if I were to look at this, and again, I'm just looking at equation 2 here, I can add 2y to both sides, and I can divide both sides by 2, and then I have a relationship between x and y, and that will absolutely help me determine what the other value is, right? So I can substitute 3x for every y I have in one of the partial derivatives. So I think we're going to do 3 examples today, and each of them has a slightly different way of solving it. And it's really looking at the situation and thinking, mathematically, what's my best approach? So this is, you're going to test your mad algebra skills to determine how to do this. So because the first partial derivative has a square in it, I'm just not going to use that. But I am going to, oh wait, yes, I can use that. I'm going to go, because I can't put it back in the second partial derivative. So I'm going to substitute this into 1. So I have 0 equals minus 6x squared. And then for every y I have, I'm substituting 3x. So I have plus 6 times 3x, yeah? Do you see what I did there? Yeah? So then I'm going to, let's see, what am I going to do next? Anyone help me? What should I do next? I need to find out what the value of x is, right? What if yes, I could, yes, let's do that. Okay, I see. We're going to take out 6. Whoops, how about that? I will minus 6. And then I have x squared plus 3x. Okay. And then, yeah, let's do that. Whoops. Wait a minute. Uh-oh. So then here I might have either oh, I know what's wrong. This has to be minus 3, right? Remember? Minus 3x, right? And then we have x minus 3. So there we have, we've factored it out fully, right? And so, well, we have 0 equals minus 6 as a possibility. Well, that's not at all possible. And then we have either 0 equals x, or we have 0 equals x minus 3. Those are our two options, right? And if we think about the context, x is the cost of a gallon of gasoline, right? So x equals 0 just doesn't make sense in the context. But here we have x equals 3. So that makes a bit more sense. We have the cost of a gallon of gasoline at $3. Yeah? Okay, so then, so this is to maximize the profit. So if x is 3, what is the value of y, the hourly wage of the house cleaning employees? I'm going to make this a little smaller so that I can show you the relationship that we found, right? Right here. We found that y is equal to 3 times x. Right, there we go. And so we're just going to be able to substitute y is equal to 3x. And so when x is 3, don't know why those are still there. When x is 3, we have y equal to 3 times 3, or 9. So we have a gallon of gas costing $3, and we have the hourly wage at $9 an hour. So this is an old example. This is American dollars. This is a gallon of gas. So it's just to allow you to think about that there may not reflect what we have here in Canada. But okay, so we are looking for a maximum. How do we know if we found a maximum? How do we confirm that? Do you remember there's two things we have to do? Yeah, fxx, sure. Okay. So let's look at so we had f at x, and that was equal to, well, it was p at x, I guess, if we want to be specific. P at x was minus 6x squared plus 6y. And so pxx would be minus 12x. Yeah? Okay. And so regardless of what value of x we substituted in there, that would be less than 0. So that tells us we have a maximum. That's the one way. We have to find pyy, and py was this. Pyy, remember you're taking the second derivative with respect to y of the first derivative with respect to y, and again it's negative 2. It's less than 0, so again that demonstrates we have a maximum. We need to find pxy. So I'm going back up to here, and I'm taking the derivative with respect to y. So that would be 6, right? And so now we can find m as well. M is equal to, right, in this case, pxx times pyy minus pxy all squared. Yeah? So pxx is minus 12x times minus 2 times 6 squared. And I'm going to substitute 3 in here because that was the value of x that we determined was the critical point, the point where we have a maximum. So minus 36 times minus 2 minus 36, 6 squared, right? So we have 72 minus 36. We have a positive number, positive 36. So because it's greater than 0, that tells us that we have an extrema of some sort. And then the pxx, pyy tells us that we have maximum specifically. Okay. So one last thing we're left to do, of course, is to determine what is that maximum profit. If we have the cost of gasoline at $3 and the hourly wage at $9, what would be that maximum profit? Okay. So we're going to substitute into the original function. So it was 600 minus 2 times 3 cubed plus 6 times 3 times 9 minus 9 squared. I think that's right. That function. So what is the maximum profit at those values of x and y? Okay, what did we have? Anyone? Um, 663. Can anyone confirm that? 600 minus, okay. Whoops. 627. Okay, do we have a tiebreaker? $627. Okay. Whoops. 627. Yeah. Thank you. So the maximum profit with $3 a gallon and $9 per hourly wage would be $627 per day, right? Profit per day. Okay. How did that look? Does it make sense? All the steps, the substitution, and how to determine if you have an extrema, what kind you have. Yeah? Okay. Seeing no concerns, we'll just go to the next question, and let's see now how we would approach this, how the language in the question is a little bit different as well. It says here, suppose that the profit of a certain firm or company is approximated by this function. Okay. You can see that the functions get quite a bit longer because you've got x terms, y terms, combination terms, and so on. X is the cost of a unit of labor, and y is the cost of a unit of goods. Find the values of x and y that maximize the profit, and then find that maximum profit at those values of x and y. So again, we're going to find partial derivatives, right? Set them equal to 0. Oops. Solve for x and y through your methods of elimination, substitution, and then determine the type of extrema that we have. So again, that's using our partial derivatives, so our second derivatives and m, those two ways. And then we're going to substitute x and y into the original function. Okay. How's that? Okay, so there we have our function. Let's begin. $1,000 plus 24x minus x squared plus 80y minus y squared. Okay, so we're going to find partial derivative, p at x. So partial derivative with respect to x. We can right away, if we like, also find the second derivatives. That will tell the story right up front. So the first derivative with respect to x, that means we're considering anything with just a y variable as a constant. So I'm looking at first derivative, 24x, the derivative is 24, minus 2x, that would be the derivative of minus x squared, and then 80x and minus y squared, they're considered constants here, and so the derivative will be 0. If I look at pxx, I'm going back to that first derivative with respect to x, taking the derivative again with respect to x, and that comes out as minus 2. And again, it's greater than 0, right? Sorry, it's less than 0, so we have a maximum point. Which for profit, that's what we're looking for, maximum profit. And we should find the second derivative with respect to y of the first derivative with respect to x. And what do we get there? 0? Good, good, good. Okay. So let's find the first derivative with respect to y, because that's what we're going to need in order to find those values of x and y. So 1,000 is the first term, derivative is 0. 24x, it has no y variable in it, the derivative is 0. Minus x squared has no y variable, so the derivative is 0. And then, yeah, we have 80 minus 2y, right? Minus y squared, that would be minus 2y. Okay, so now we can pick out our two first derivatives. We set them equal to 0. Now, do we notice anything about these two partial derivatives? Should we use elimination, substitution, or, well, graphing to solve these? What do you notice? Substitution, okay. If we look at the two partial derivatives, do we have both of the variables represented? Yeah, we can actually directly find x and y. Yeah, that's super. So here we have 0 equals 24 minus 2x. We add 2x to both sides. We divide by 2, and we find directly that x is 12. Right? And we can do the same thing with the second partial derivative. We have 0 equals 80 minus 2y. We add 2y to both sides and divide by 2. And we find that y is equal to 40. Yeah, so this is a little bit easier even than the last question where we did have to use the substitution method. Okay, so now we have determined that we have a maximum. We've found the second derivatives xx, yy, and now we need to substitute those into the original function here. So we have 12 units of labor and 40 units of goods. And those are the values of x and y that will maximize the profit. And so now we substitute those values into the original function just to determine what that maximum profit will be at those levels. Okay? Whoops. Okay. So p at xy, I'm just reminding you of the function. And we're evaluating that profit function at 12 and 40. Okay. This is 1,000. Okay. George says 1844. Can anyone confirm or deny that? 2,744. Okay. We have another value. Who's going to take the break the tie here? Anyone? Okay. Oh, there's someone. Fatima says it is 2,744. I'm wondering if, and I'm going to ask George perhaps right here, this is often a place of error where you are squaring the value and then applying the negatives, the subtraction of the negative sign. Did you maybe do that? I think so. Let's see, 2,744. Maybe. I think that might be. Okay, thank you. Okay, so how was that? Oh, I'm sorry. That was me. I put 100 up. So yeah, you were out by 900. That's exactly right. So sorry. How did that go? Okay. You have a function, two partial derivatives, second derivatives, determine what extrema you have, find your method of solving for x and y, depending on the situation, what your partial derivatives would call for, and then substituting those values of x and y into the original function. Yeah? Okay. It's a lot of math, but it's not hard math. It's just keeping track of your negative signs and keeping in mind what variables are kept constant and so on. Okay, let's try one more and then we're going to learn about a really cool extension. Okay, so keep trying along as we go so that everyone is working on the question as we go along and you know where you get stuck and we can figure it out right away. So here it says the total revenue in thousands of Canadian dollars from the sale of X spas and Y solar heaters is approximated by this function. So again, it's a revenue function. Businesses want to maximize their revenue. So we're looking for the number of each that should be sold, each type of product, spas and solar heaters, that should be sold to produce maximum revenue. And then we're determining what that maximum revenue will be if those numbers of items are sold. Same idea, okay? So the first thing we're going to do is find the two first partial derivatives. And then let's see what strategy we need to solve them. Yeah? Okay. Gonna write it. Whoops. Who knew at the beginning of semester that you would be so good at taking derivatives and doing all these amazing things? Did you ever think that you would be doing this? Okay. So the first partial derivative with respect to x, keeping y constant, we have 74 minus 6x minus 5y. Is that right? Yes. And then first derivative with respect to y. So we're considering the x variables constant. I have 85 minus 10y minus 5x. Does that seem right? Always good to double check your work before you go on to the next big step. The worst thing is to find an unreasonable or unlikely answer at the last step you make and think, where did I make the first mistake? So always double check. Is that right? Those two partial derivatives? Yeah? Okay.
Yeah.
So now remember, I'm setting them equal to 0, each of them. And what I'm going to do, and you'll see here, is I'm going to just rearrange the terms so that I line up the x's above or below the other x variable and the y variable below the y variable, right? So we're not getting confused. So I now have minus 6x, and then below that in the second partial derivative minus 5x, so they're lined up. And this allows me to consider if we're going to be doing elimination, substitution. So again, when I'm looking at substitution, it's usually the best strategy when you have a coefficient of 1 in front of one of the variables, and we don't have that. So I'm looking now for elimination strategy, and I'm looking through the coefficients, and I'm saying, well, minus 6 and minus 5, well, those are distantly related. So I move on to the y variable, and I say, well, minus 5 and minus 10, right? We're looking for multiples or factors, and I see that minus 5 is related to minus 10 by a factor of 2, right? So I think I'm able to multiply the first partial derivative by 2, and then we can eliminate the y variable. Does everyone see that? How that might be a good idea? Right? 2 times that first. So I have 148 minus. We could also multiply by minus 2. That might work too. Right? What do you think? Minus 2. let's do that. And then I'll be able to add. And then the second partial derivative, I will just leave it as it is. And now I can add those two partial derivatives together. So 0 plus 0 is 0. I have minus 148 plus 85. So minus 63. Is that so? 12x minus 5x, right? We have 7x. And of course, our whole purpose was 10y plus minus 10y. That's 0. That eliminates that variable. So now I can add minus 63 to both sides, divide by 7, and I find that x equals 9. So the number of spas that should be sold to maximize the revenue would be 9. Yeah? So how many solar heaters? I take this value of x is 9, substitute it into one of the partial derivatives. So maybe I'll substitute it into 2. I have 0 equals 85 minus 5x minus 10y. Substitute x is 9 there. Okay. So then I have so I can add 10y to both sides, and I have 40 over here, and then I would divide both sides by 10, and I would find y equals 40, or sorry, y equals 4. So I have x equal to 9 and y equal to 4. So yes, in order to maximize the revenue, I would sell 9 solar heaters, 9 spas and 4 solar heaters. So I take those values back up into the revenue function, substitute them into the original function, and determine what that maximum revenue would be at those values. So, okay, 515, we have agreement right out of the gate, 515, okay. Okay, how does that look for you? Does that make sense? We've gone through a few with kind of different solutions at that solving for x and y state, but I think we've done some pretty good practice. Is it making sense?
Yep.
Okay. So the next cool thing that we can do with partial derivatives is determine a maximum or minimum value when we have a constraint. So some kind of restriction on our business, what we have to achieve in our business. And we do that using something called a Lagrange multiplier. It is so cool and kind of one of my favorite things. So a Lagrange multiplier is another type of variable, I guess. It looks like this. To me, it looks like a little giraffe. And that would be the Greek letter lambda. And that multiplier actually behaves kind of like a piece of Lego, where you're combining one piece of Lego with another. And that multiplier allows us in math to combine a function with a constraint, some kind of limit on your business. How cool is that? So imagine that you are given the task of determining the smallest soup can you can create, because you want to save metal. So you want to create a soup can using the least amount of metal possible, right? So you might design a teeny tiny soup can like this. And you think, look at me. I designed a teeny tiny soup can. How great am I? And then you show it to your boss, and your boss says, how can I put 10 ounces of soup in that teeny tiny soup can? Back to the drawing board you go. So the task of finding a soup can, or minimizing the amount of product you use, is constrained by the fact that the soup can has to be big enough to actually fit the product. Do you see how those two things come together? And so this Lagrange multiplier actually allows us to combine a function such as a profit function or a revenue or cost function with this kind of constraint. Like, yes, you have to minimize your profit, but wait, you also have to meet this criterion. Okay, so we use something called a Lagrange function. So essentially a Lagrange function, and here's what someone was asking earlier, are we going to use more than two variables? So kind of a variable. The Lagrange function takes the original function and connects it using that Lagrange multiplier to, so this is the original function. Lagrange multiplier connects it to the constraint function. Okay? So how do we know when we need to use this? How do we know when we have a constraint in place? You'll always find it in the question. It will say you must produce this much, or this has to be taken into consideration, or something like that. So we put those, the constraint function together with the original function using the Lagrange multiplier. Then we are able to expand the Lagrange multiplier with the constraint function, take first partial derivatives, and then solve for x and y. So that would determine what those values would be in order to find the extrema of the original function. Okay, it's very cool, and I think it's quite fun. So let's have a look at this question. This is the first one. The profit from the sale of X units of, do people say radiators or radiators? Anyway, radiators from automobiles, and Y units, radiators? Okay, I'll use that. The profit from the sale of X units of radiators from automobiles and Y units of radiators from generators is given by this profit function. Okay, there we have it. It says find the values of X and Y that lead to a maximum profit. Okay, that seems familiar. We've already seen that. But the next bit is how we know there's a constraint. The firm must produce a total of 6 units of radiators. That tells us that we have a constraint. Okay, We must produce 6 units. So what we're determining here is what our productivity balance should be in order to maximize this profit. Okay, so how do we write that? I'm going to write this profit function again, just to write it a little bigger. Writing this down also kind of helps to embed it in your brain. And so X is the radiators for autos and Y is the radiators for generators, and we must produce 6. So this is what that would look like, right? X and Y must equal 6. In order to use the Lagrange function, this constraint has to be written with respect to equaling 0. So it must be equal to 0. X plus y minus 6 equals 0. Okay, so this is our g at x function, our constraint function. This is our regular function, our multivariable function. So now we combine that into the Lagrange, the big Lagrange function, and we start to solve. The formula for the Lagrange multiplier function will be on your formula sheet, and of course you're writing it down now, so you'll be able to have it, access it for the final exam, okay? So let's set it up. Okay, minus x squared minus y squared plus 4x plus 8y minus lambda times x plus y minus 6. Yeah? Before we take any partial derivatives, we want to expand that bracket at the end there, and we're going to remember that this negative sign, negative lambda, it has to apply over each of the terms in the bracket, remember? So let's do that first. So minus lambda x minus lambda y plus 6 lambda. Yeah? Okay, I gotta make it look more like a lambda and less like an x. There we are. Okay. Are we good so far? Then, now because we have 3 variables, we're actually able to find 3 partial derivatives. In order to solve for x and y, we're really only going to be using our partial derivatives with respect to x and with respect to y, but we should find all 3. So let's start with the first derivative with respect to x. Same thing we did before. Look at each term, see where we have an x variable, and then we know we have to take the derivative. If we don't have an x variable, everything else is considered a constant. So minus x squared, the derivative is going to be minus 2x, minus y squared, the derivative is 0, plus 4x, the derivative is 4, and then we have minus lambda x, so the derivative will be minus lambda. Yeah? We do the same with our first derivative with respect to y. See how this is coming together? Right, minus minus 2y comes from minus y squared. 8 comes from 8y, and minus lambda comes from minus lambda y. If I take the derivative with respect to lambda, I have minus x minus y plus 6. Okay. I'm really concerned about these two. We're solving for x and y. I'm going to set them equal to 0. 0 equals minus 2x plus 4 minus lambda, right? And 0 equals minus 2y plus 8 minus lambda. So if we look at the first partial derivative, we have an x variable and a lambda. On our second partial derivative, we have a y variable and a lambda. So it makes things quite complicated as far as elimination, substitution, or graphing. So I'm going to just give you a little hint. If we have, I'm going to make, so 1, I'm going to add lambda to both sides. And 2, I'm going to add lambda to both sides. Okay? So what I have is 2 terms that are equal to lambda and another 2 terms that are equal to lambda. If they are both equal to lambda, they must be equal to each other. And I'll give you an example of where we would see that. We have 4 plus 1 is equal to 5, yeah? We have 2 plus 3 that is also equal to 5. What that means is that 4 plus 1, which equals 5, must equal 2 plus 3, which also equals 5. Does that help it to make sense of how we can set those 2 sets of terms equal to each other? It's fun, right, Deepak? Nice. Just to prove that this is a reasonable assumption or a reasonable next step. So here's what we do. We're going to set those 2 equal to each other. Right? If I were looking at this now, I would say, I am going to try and get x and y by itself. I'm looking at a substitution, and I'm looking at the coefficients thinking, if I just divided by minus 2, that may simplify my life a bit. So I'm going to divide by minus 2. So I'm going to have x minus 2 is equal to y minus 4. Oops, I have to put the minus in there. Tell me if that makes sense. X minus 2 equals y minus 4. Yes? Okay, I think that looks right. Does it make sense? I have x over here. I'm adding 2. Sorry, I'm adding 4. Does that work? X equals y plus 2. Wait for it. I added 4 to here. That made it 2. Oh yeah, we could do the other way too. That's cool. What do you think? That works? So instead of finding a value of x and y directly, we're finding again a relationship between x and y, right? So now what do? I'm reminded that our constraint says that x and y must equal to 6, right? So if I took this value of x plus 2, because that equals y, and substituted in for the y that we have in the constraint function, x plus 2 is equal to 6. I have 2x plus 2 equal to 6. I have 2x equal to 4. I have x equal to 2. How's that? And if x is 2 and x plus y equals 6, then y must equal 4, right? How cool was that? Very cool indeed. So we have found that in order to maximize the revenue, let me just look and make sure that's our function. We're gonna way up here. Look at the math. Oh, profit. In order to maximize our profit, this company is going to need to sell 2 radiators for automobiles and 4 radiators for generators. Our last and final step is going to be finding out what that maximum profit is by substituting those values of x and y into that original profit function. Okay, so P at 2 and 4. That's our last step here. Okay. Okay. Not yet. 3 o'clock, right? Thanks, Abdullah. Oh my goodness. 20? Did we get 20? Same? Okay. Okay. I have one more question to do, I think, with you. Let me. How are we doing with those? So, function, constraint, right? First derivatives equal lambda, set them equal to each other and solve. right? Okay. Are you ready to do one more of this type? I should say. Yeah? Okay. It's good. It'll be good practice. You can see. Okay for 2? I think so. We still have half an hour or so. Yeah, we're okay. Okay, whoops, I'm gonna go back. Okay, so here we have a cost function representing the production of small clocks and large clocks. And this is the cost function. It says that a total of 36 clocks must be made. And it asks, how should production be allocated so the total cost is minimized? So here we see another sort of variation in the language in the question. Production allocation. How many small clocks and how many big clocks are we going to be producing to minimize the cost? And then what's the minimum cost? So let's find let's find our constraint function. And again, 36 clocks must be made. The constraint function is x plus y equals 36, written to equal 0, right? Set up our Lagrange function. Whoops. Minus lambda times x plus y minus 36. Okay. Again, we want to expand the bracket, wisely remembering we're applying that negative sign to all the terms in the bracket. I'm taking each step by step so that I'm not missing anything for you. So remember that last one is plus 36 lambda. Okay, now we take the 3 partial derivatives, one with respect to x, one with respect to y, one with respect to lambda. Okay, so 7x squared, the derivative is 14x plus 12y minus lambda, I think. Plus 12xy, the derivative is plus 12y. Super. Okay. Derivative with respect to y of xy lambda is equal to 12x plus 28y minus lambda. Is that right? How does that look? Okay, then remember that, oh, we have to do our one last with respect to lambda of xy lambda is minus x minus y plus 36, yeah? Okay. Then again, we want to remember that relationship. We're going to set these 2 partial derivatives equal to 0. Add lambda to both sides. equality. And then we can look at that relationship again, that if these set of terms equal lambda and this set of terms equal lambda, they must equal each other. So we set them equal to each other. This is kind of cool, eh? And I like to work in positive values. So I'm going to subtract 12x from both sides, and I'm going to subtract 12y from both sides. That's going to leave me on the left side of the equality with 2x equals to 16y. Is that right? So x is going to equal 8y. Is that right? I'll let you confirm that or question that. Okay, is that right so far? Is everyone there? Yeah, oh, good, yay. Okay, and so far so good. And then we need to look at what our constraint function was, and it was, wait for it, 36 clocks, was it? 36 clocks, okay. So our constraint was x plus y must equal 36, but we found that x is equal to 8y, so we substitute that in here. So we add those together and we find that y is equal to 4. And again, if x plus y equals 36 and y is 4, then it follows that x must be 32. So in order to minimize the cost, we want to produce x small clocks and y large clocks. I know, it is a thing of beauty, isn't it? It's like math. Yes. So cool. So we go back up to our original function, because our next and final step would be to evaluate that cost function at 32 and 4. So we find out what the minimum cost is at those values. Okay. $8,938. Can anyone confirm that? Yep, okay. Super. $8,938 is the minimum cost to produce 32 small clocks and 4 large clocks. Awesome. Okay, one more, because it's a little bit different and actually it's also fun. 2. Are we okay? Then I'll let you go to write your little quiz. So the quiz today is worth 3.33% of your final. 8 questions. You've got this. Okay. So here's the last question I'm going to do with you. It's called the Cobb-Douglas production function. And you'll remember that we worked with a function before, a productivity function, right? Where it is a factor of units of labor and units of capital. So this is exactly that function. But we're looking at it now with respect to maximizing production with a constraint. So it just is a little bit more of an extension of what we've been doing and a little bit more challenging. So that's why I really want to walk you through this. So this Cobb-Douglas production function represents X as the number of units of labor and Y as the number of units of capital required to produce so many units of the finished product. Here's the constraint part. Each unit of labor costs $8, each unit of capital costs $12, and you have $80,000 that are budgeted for this production. So determine how that amount should be allocated to maximize production. So how should that $80,000 be utilized? Okay, so let's think about this just as we've been doing the last couple of examples. We need to establish the constraint function first, and we have X is the units of labor, and every X costs $8. Okay, so we have 8X. We have Y being units of capital, and every unit of capital is costing $12. So plus 12Y, and we have $80,000 budgeted. So it's $80,000, yeah? Yeah, okay. So that is our constraint function. We need to set that or make that equal to 0 in order to use our Lagrange multiplier. So we'll just do that before we forget. And then we set up the Lagrange function. So we have f at xy lambda is equal to the original function minus lambda times that constraint function. 8x plus 12y minus 80,000. Expand the bracket down here, remember? Okay, now we've got a few more things to remember. Minus 8 lambda x minus 12 lambda y minus 80,000 lambda. Okay, now we tackle the first derivatives. Even though the function looks a little weird and the constraint function looks a little different, we're literally being able to do the same things that we had done before. So the first thing, yep.
Sorry, Emily.
Hi, Kevin.
Should the 80,000 be positive?
Oh, yep, it should be. Thank you.
Okay.
Oh my goodness.
No, I was concerned I was wrong.
Yeah, no. Thank you. Yay, saved. So now we're going to find the first derivative with respect to x. Thanks, Kevin. Okay, so if we look at this 80x to the 0.7, y to the 0.3, that is one polynomial, right? It's not separated by an addition or subtraction. So when we're looking for the derivative with respect to x, we consider y and lambda the constant. So we have 80. We have y to the 0.3. And then we have 0.7. So remember, we're looking at this type of still x to the n. The derivative is nx to the n minus 1. That's what we've been doing all along. Whoops, so here we have 0.7. Whoops, that didn't work so well. 0.7, and we have x to the 0.7 minus 1. That's negative 0.3. Yeah? And then minus 8 lambda. Yeah? I'm going to, simplify this. So I have this as my uh, 56, I guess. Does that make sense? 0.7 and then 0.7 minus 1. Simplify by multiplying. Yeah, I think that's good. I'm going to, I'll just go to the next thing, which is I need to find the partial derivative with respect to y. Are we okay so far with this? Yeah, okay. Wow, all right, let's try it. At y of xy lambda. So I have 80 again. I have x to the 0.7 because that is they're the constants in this case. We're keeping x constant. And then the next part of the polynomial, I have y to the 0.3. So I'm multiplying by 0.3. And I have y to the 0.3 minus 1, minus 0.7. And you're going to notice a pattern. Math is about finding patterns, right? Look at that. Minus 0.3, positive 0.3, positive 0.7, minus 0.7. Yeah, that's cool. It's like a bit of magic right there. Oh wait, and I forgot the lambda part. So I got so excited about that. I have minus 12 lambda. Is that so? Yes. Okay. So now I would set those derivatives, partial derivatives, equal to 0. 0 equals, oh wait, I'm going to first simplify that, right? I have 80 and I have 0.3, so I should do that simplification first before I move on. So 80 times 0.3, that's 8 times 324. X to the 0.7, y to the negative 0.7 minus 12 lambda. Yeah? Okay. So I'm looking at two partial derivatives. This one here and this one here. And how I'm going to find values of x and y. I'm going to set this equal to 0. And remember in our last examples, we had something equal to lambda and something else equal to lambda. Well, now here I've got minus 8 lambda. But I'm going to look at that coefficient in front of the polynomial, 56, that value 56. And I'm going to notice a relationship between 8 and 56. 56 is a multiple of 8, right? So if I divided by 8, we could be all right. I think this will help us from here. So I have 0 is equal to 7x to the negative 0.3, y to the positive 0.3 minus lambda. So I divided the two terms by 8. Yes. Then I take the first derivative with respect to y. And again, I'm going to notice that, because I'm trying to get lambda kind of by itself, I notice that 24 is a multiple of 12. Yeah, so I can divide by 12. Yes, let's do that. 0 is equal to 2 x to the 0.7, y to the negative 0.7 minus lambda. Okay. So now we're kind of in the same place we were before with other questions, where we have lambda equal to something in that first partial derivative. And in that second partial derivative, we also have lambda equal to something. So again, we can say, well, if this is equal to lambda and this is equal to lambda, they must be equal to each other for those equalities to be true. So we can set them equal to lambda. And we'll worry about the next step next. Don't worry, let's follow the math. Even if we got to here, that would be awesome. Don't give up. Okay. Now what? Okay, I'm going to give you a couple of asides. I like to call these like just-in-time bubbles, a reminder of our past math. And I'm going to remind you that if we had 1 over x cubed, that is equivalent to x to the minus 3. Do you remember that? Does it sound familiar? Yeah, okay. And I'm going to say, do you remember if we are multiplying exponents with the same base, we're able to add the exponents together? So x squared times x cubed is equal to x to the 5th. Do you remember that? Yeah, okay, it's all coming back. And conversely, if we had x to the 5th divided by x cubed, as long as they have the same base, then we subtract the exponents. So that's our little rules of exponent lesson, because it becomes relevant here when we look at negative exponents on both of those, that x variable and the y variable. So what if we rearranged that equality so that it was like this? I just made that a fancy y because I started to write something else. Okay. Then what should we do, or what could we do? what if we multiplied by x cubed, kind of cross multiplied, and we multiplied by y to the 7th. Oh, sorry, y to the 7th, it's y to the 0.7, sorry. Now let me just check to make sure that's right. Yes, okay, are we right? So I would have 7 y to the 0.3 times y to the 0.7 equal to 2x to the 0.7 times x to the 0.3. Look, you guys, nobody told me that was, okay, there we go, 0.3. Thank you. Thanks, Warda. Okay, so now I can use those power rules, sorry, exponent rules right there, where I am multiplying exponents with the same base. So I add the exponents together. So this gets interesting. So I have 7y, and I'm adding them. I'm just going to show you how I'm going to do that. Right? Is equal to 2 times x to the 0.7 plus 0.3. Right? Kevin, 7y equals 2x. Mic
Yeah.
drop. How cool
I got
is
it a completely different way though. That's why I was really.
But did you get that? You got it a different way?
Well, I just saw that it was like, the negative 0.3
Yeah.
onto the 7. So I'm like, well, if you add, 0.3 to this and 0.3 to the other thing, it becomes, well, you now have a whole variable on this side. That variable on the other side disappears, and vice versa.
Exactly. Yeah.
And I mean, if it wasn't that they added up so evenly with 0.3
I
and
know.
0.7, I wouldn't have thought to do that. And then I was looking up it, and I'm like, I figured we were getting to the same place, but I'm like, am I doing this right? And then I see everyone else putting stuff, and I'm like,
It's like math-a-magic, isn't it?
yeah, like I guess I don't think the way I came to the answer is the wrong way, but I don't know if it would work if things were more complicated. I think your way is a lot better.
There are many ways to get to this point, right? This is one way to get there. So honestly, when you are flexible with numbers and you kind of have that sort of foundational idea, there's lots of ways to get to this place, this relationship.
Yeah, I just used
Brilliant.
Subtraction because
Yeah.
I'm really lazy about it. I don't want to do division or anything.
No, not, and yeah. So what we find then, and I'm going to just divide that 7 by 2. So x is equal, whoops, see, look at that. I put that in there. That's not right. 3.5y. X is equal to 3.5y. So now, just like in the other questions that we had done with respect to the Lagrange multiplier, we go back to our constraint function. And our constraint function said $8 for every unit of labor, $12 for every unit of capital, and our allocated budget is $80,000. And so now we have x equal to 3.5y. So I can substitute that value in there. Right, so 8 times 3.5 will be 28y plus 12y is equal to 80,000. This is 40y equals 80,000. And so our y equals 2,000. So y is our units of capital, so we should in order to maximize our production, we're going to have 2,000 units of capital. And remember, let's go back to that simple relationship that x is equal to 3.5y. We don't have to go back to our constraint function. And so we can substitute. Now we have an actual value of y, we can substitute that into that relationship and we can find that x is 7,000. So in order to maximize our production, we would invest 7,000 units of labor and 2,000 units of capital. And we would find that maximum production by substituting those values in. Whoops. Let me find that function again here. 80 times 7,000 raised to the power of 0.7 and 2,000 raised to the power of 0.3. Yeah? 384,563.10. Okay, anyone confirm that? Nice, okay. $384,563.10. These are big dollars. So that last question was a bit more complicated because the function looked a bit different, but we know we have those skills in order to take the partial derivatives. We know our rules of exponents. We just have to be reminded sometimes how they work. And yeah, I think that went okay. Yeah. So you will have, just going to close this up for a moment. Stop screen sharing. And I will